Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about how to predict whether a chemical reaction or physical process is spontaneous or non-spontaneous. Okay, now the first thing we should talk about, what does it mean to be spontaneous? If a chemical reaction is spontaneous, it means that it will occur without outside intervention. You don't have to do anything to make the reaction happen. It will just naturally take place. And the reason why I have a picture here of fire is because combustions, for the most part, tend to be spontaneous. Think about like if you have some wood and you're going to build a campfire. Once you light it and you start it burning, it will just naturally keep burning, right? You don't have to do anything to keep it burning. Once it starts, it just burns. Or let's say that you have like a candle. Okay, so you got your candle and you've lit the wick on it. Once you get it started, that candle will just continue to burn without any outside interaction or outside intervention, right? It just naturally keeps going. So if a chemical reaction just naturally happens, we call it spontaneous. Okay, think about your car. Think about the car that you want in the future. Think about your bicycle. Think about something made out of iron. You know that iron naturally or spontaneously rusts, right? It's a reaction that'll happen without you doing anything to make it happen. Actually, we spend quite a bit of time trying to prevent that spontaneous reaction. It's the reason why your car or your bicycle is painted, right? So your iron is here. It really wants to rust. But if you put a coat of paint over the top, it prevents the spontaneous reaction from happening. Mainly because you're separating the reactants, the iron versus the oxygen in the air and the water, right? If they can't get to the iron, the reaction can't happen. So what we'd like to be able to do is we'd like to be able to look at the reactants and we'd like to be able to look at the products and decide if a chemical reaction is going to occur or not, whether it's going to be spontaneous or not spontaneous. Now, the way that we're going to decide, we have to look at how much heat is involved versus how much disorder is involved. Okay, so we can determine it by looking at the enthalpy change. That's the change in the amount of heat versus the entropy change, which is the change in the amount of disorder. Now, you've done some chemistry before at this point if you are up to predicting spontaneity. And you should realize by now that in the world of chemistry, a lot of terms that we use in the same sort of problem tend to sound very similar to each other. And this is one of those cases where it's enthalpy change for heat and entropy change for disorder. Oh, and there's a little bit of a typo there. See, that's copy and paste got me. That should have been delta S. Because the symbol for enthalpy change is delta H, and the symbol for entropy change is delta S. Okay, so cutting and pasting kind of got me there. But again, these two words sound very, very similar, so you really do have to be careful that you're using the correct one at the correct time. Okay, so let's think about each one separately. So if we want to talk about the enthalpy change, the change in the amount of heat. So you've got a chemical reaction, you've got a physical process. As it happens, it's either going to release heat into the environment or it's going to pull heat into the system, right? So it's going to be exothermic heat out or endothermic heat going in. Now, the way the universe works, the entire universe wants to head towards low energy, right? Think about it after you've had a hard day of school, you've been out working on your courses, right? When you come home, are you feeling high energy or low energy? Probably low energy, right? You just want to sit down and take a little bit of a rest. The entire universe is like that. The entire universe wants to sit down and take a rest, right? The entire universe is tending towards low energy. So any chemical reaction, any physical process that reduces the amount of energy is going to tend to be spontaneous. It's going to tend to be the one that happens. So that's what we've got here, right? Substances tend towards a lower state of energy because it does give it increased stability. The lower energy you have, the more stable you are. And that's why exothermic reactions tend to be spontaneous. Because if you're an exothermic reaction, you're giving heat away, right? Exothermic means heat's given away. So if you are giving heat away, then the amount of energy that you have left is going to drop. So exothermic reactions give their heat away, and then what's left, the system, is going to be lower energy. Lower energy, more stable. Lower energy is what the universe wants. So if you have an exothermic reaction, it does tend to be spontaneous. Now, there are some exceptions because you're not just looking at enthalpy change, you're also looking at entropy change, right? There's two different things going on. But exothermic do tend to be spontaneous. So I should underline that because that is important. All right, let's say now that we want to talk about the entropy change. Okay, and I do have it as delta S here. Copy and paste didn't fail me twice. So your entropy change is the change in the amount of disorder in your system, okay, randomness. And the universe loves disorder, right? I have a separate video that talks about how do you predict the amount of entropy change. So if you haven't seen that video, if you're still having a little bit of trouble of predicting how much entropy change you have, you might want to pause this one and go back and take a look at the video that talks about how you predict entropy change. And the reason why I bring that up is the example that I talked about in that video was like your room. You go into your bedroom, you clean it up, it is like pristine, you've got everything organized. And then you just kind of live your life for the next couple of weeks. Does it naturally stay organized, or does it naturally become disorganized? Well, the obvious answer is that it becomes disorganized, right? Nature likes disorder, so things naturally become disorganized. So anything that's going to increase the amount of disorder, anything that's going to increase the entropy, right, your delta S is going to be positive, is a good thing. So reactions that increase disorder are also generally spontaneous. Now again, we use the word generally, which means mostly, because there will be some exceptions. There will be some reactions that increase the amount of disorder, but they're not spontaneous because you have to consider both, right? This would be like if you're voting for somebody and there's only 2 people allowed to vote. Enthalpy change, you can either vote for spontaneous or you can vote against spontaneous. Entropy change, you can either vote for spontaneous or you can vote for non-spontaneous. Now, if both of these say, yes, we both think it should be spontaneous, then the reaction will be spontaneous. If they both vote and say, nope, I don't think that it's going to be spontaneous, then it's never going to be spontaneous. The issue happens is when you get sort of mixed results. When one of them says, yes, I think this reaction should be spontaneous, but the other one says, no, I don't think it should be spontaneous. And then you have to decide which vote counts more. So then you have to decide, does the vote for spontaneity count the most, so it is spontaneous? Or does the vote for non-spontaneous count more, so it's going to be non-spontaneous? And in some of these cases, you're not going to be able to tell, right? It's just going to be an I don't know. Okay, so let's take a look at a couple of examples. So for each of these chemical reactions, I would like to predict whether it's going to be spontaneous or non-spontaneous. So for each of them, I'm going to need to decide, is it exothermic or endothermic? I'm going to have to decide, is there more disorder or is there less disorder? Okay, so let's talk about endo versus exo. That's probably the easiest. If your energy is built straight into your chemical reaction, if it is part of the product side, then it is going to be exothermic. So exothermic if it is on the product side, right? Reactant, product. If it's part of the product, you are producing heat, so it is going to be exothermic. If your energy, though, your heat, is on the reactant side, that means it is going to be endothermic. Because in order to make this reaction happen, what do you need to put in? I need to put in some nitrogen. I need to put in some oxygen. And I need to put in some heat. Right? So if it's over here on the reactant side, that means that I am adding it. And if I am adding it, that's endothermic, right? If heat is being added to the system, that's endothermic. Same thing for this last one, right? My heat here is on the reactant side. So I'm adding it like a reactant. So this one here would be endothermic. Okay. If you have heat built into your equation, those are probably the easiest ones to tell exo versus endo. Exothermic, the heat is a product. Endothermic, the heat is a reactant. And so for each of these, now I have a vote, right? We said if you're exothermic, then you are most likely spontaneous. Okay, so this is a vote for yay, spontaneous. But if you're endothermic, right, if your heat is going in, that means the energy level of your reaction is going to go up, right, because you're putting heat in. High energy, we said, that's not favorable. So for endothermic, these are both votes for no. Both of these are saying, nope, I don't think that reaction's going to happen, right? That's a no. Now, when you're doing these, you're not just looking at the enthalpy change. You also have to talk about the entropy change, the disorder. And like I said just at the beginning of the video, if you haven't watched my other video that talks about predicting entropy changes, you should pause and go back and look, because that's what we're going to use here. Okay, so if we are going to predict entropy changes, for this one here, we said that in any chemical reaction you should count. Because if you go from low number of reactants to high number of products, then that's a positive change in entropy. If you go from a high number of reactants to a low number of products, then that's a decrease in entropy. For this first reaction, it's not really an issue, because you start with one sodium hydroxide solid and you end with one sodium hydroxide aqueous. Right? So you start with one, you end with one. Start with one, end with one, no change. The other thing that I'm going to take a look at here is the phase, whether it's a solid, a liquid, a gas, or aqueous. Because depending on which phase you're in, that also determines how much disorder you have. So if I look at the sodium hydroxide, this is a solid. Solids are very, very organized. All of the little particles all line up. None of them are allowed to move from their location. They are allowed to vibrate a little bit, right? A little bit of vibration, but they can't really move. If you're talking something that's aqueous, I have just taken all of these sodium hydroxides and put them into my beaker. I then added some water, right? That's what it means to become aqueous, so you've added some water. And they've just become intermixed. Right? All of my sodium hydroxides are now random, and they're mixed in with a bunch of waters, which are also totally random. So when you're talking about disorder, when you're talking about entropy, solids have very low disorder, right? They are very organized, very low disorder. But when you talk about something being aqueous, it's now completely mixed up with a second substance, right? It's completely mixed up with water. So now this is way more disordered. So you're going from low entropy to high entropy. That's an increase. Your change is positive. You are gaining entropy. You are gaining disorder. So for this one here, the change in entropy, delta S, is going to be positive. You are increasing the amount of disorder. And we said just a minute ago that if you increase disorder, you tend to be spontaneous. So this is going to be another vote for spontaneous. Now, there's only two votes, right? There's two people voting in this election. First one says, yay, spontaneous. The second one says, yay, spontaneous. And so if they both vote for spontaneous, then spontaneous wins. So this first reaction here will be spontaneous. And if you've ever spent any time in the chemistry lab, you know that sodium hydroxide is one of our favorite bases. You throw sodium hydroxide in water, and it just naturally dissolves. It spontaneously dissolves. All you need to do is put the sodium hydroxide in the water, and it just dissolves all by itself. You don't have to do anything. Spontaneous. All right, if we move on to the next reaction. Now, we've already got a vote against here, right? So best we can do is maybe like a tie, one vote down, one vote up. Or maybe they're going to be both votes down and this thing will never be spontaneous, right? But you have to look at entropy. So first thing we're going to do is count. Over here on the reactant side, I've got one nitrogen and I've got two oxygens, right? There's one of these and two of these. So I have a total of 3 particles. Over on the product side, I have 2 NO2s. Okay, already I can see that this is not going well because we said that the more of something you have, the more disorder you have. So if I have 3 reactants, that's some disorder. If I've only got 2 products, that's much less disorder. So this is going to be a drop. So I now have a delta S being negative. Okay, so negative delta S's are bad. But I'm not finished, right? The delta S requires a lot more work from you. You are going to count the number of reactants versus products, but you also need to consider whether they're solids, liquids, or gases. Now for this one here is not bad because you did start with a gas. Out of solids, liquids, and gases, gases move the fastest and they have the most chaos, the most disorder. So you're starting with a gas that has lots of disorder. You're starting with a second gas that also has lots of disorder. And what's your product look like? It's a gas. It's got disorder. So your product is also going to be super disordered. So if I look at their state, solid, liquid, or gas, I find out that in the beginning, everything was a gas, so lots of disorder. And I find at the end, they're still gases, lots of disorder. So because it goes from gas to gas, this is not really going to contribute anything. So the only thing that I really had to think about was going from 3 reactants to 2. Okay, this one over down here, the delta S, really this one would be no change, right? Because you're going from gases to gases. So if you've got a negative and a no change, they basically add up to give you a negative. And we said, if your change in disorder is negative, if your amount of disorder is decreasing, that's a bad thing. The universe loves chaos. It loves disorder. So this is a vote against. So for this reaction here, because it's endothermic, we're saying, nope, probably not spontaneous. Because the entropy change is also negative, we're saying, probably not spontaneous. So if both things vote for non-spontaneous, then this reaction is going to be non-spontaneous. Which means if you mix some nitrogen gas and oxygen gas together, they are never going to spontaneously or naturally form nitrogen dioxide. And again, we know this. Okay, you're sitting here watching the video, you're breathing. Breathe with me. When you breathe in, our atmosphere contains nitrogen gas. There's a lot of it. There's like 78%. When you breathe in, there's also lots and lots of oxygen. There's like 8% oxygen. So you are now surrounded by nitrogens and oxygens, but there's probably no nitrogen dioxides where you're currently sitting because this reaction does not naturally happen. It does not spontaneously happen. All right, let's move down to the third one. We've already said that it's endothermic. Endothermic is a vote against. I do need to figure out now entropy changes. So the first thing I'm going to do is count. Second thing I'm going to do is look at the phases. So if I count here on the reactant side, I've got 1 carbon dioxide, I've got 1 hydrogen gas. So 1 plus 1 is 2 particles. If you look over here on the product side, I've got 1 carbon monoxide, I've got 1 water, so 2 particles. So if you go from the chaos of 2 particles to the chaos of 2 particles, have you really changed anything? Not really. So if you go from 2 to 2, this is saying the delta S probably not going to change, no change. Okay, if you look at the states, solid, liquid, gas, aqueous. This is a gas and this is a gas. So here on the reactant side, you have highly chaotic gases. You have another highly chaotic gas. And if you look on the product side, what do you got? I got a highly chaotic gas. And I've got another highly chaotic gas. Right? You're going from gases to gases. Highly chaotic gases at the beginning. Highly chaotic gases at the end. Did that change the amount of disorder? Again, no. So when you look at the phases, again, no change. So based on the numbers, the entropy is not going to change. Based on the phases, it's not going to change. So overall, I'm thinking it's like, it's not really going to change. So this is a bit of a unique situation. You have 2 people voting in the election. The first person says, no, not spontaneous. And if you've got no change, the other person is saying, I abstain. I am not going to vote. So instead of voting for or voting against, they're like, nope, just not going to vote. So if you have only 1 vote and that 1 vote is for no, then this reaction would also be non-spontaneous. All right, let's try another example. Let's say we talk about this one. This is propane plus oxygen giving you water and carbon dioxide. If you have a propane barbecue, that's the reaction that's happening. Now, if I want to know if that's spontaneous or not, 2 things I need to look at. Does the reaction, is the enthalpy negative? Is it an exothermic reaction? Is the change in entropy, the disorder, positive, right? So is it exothermic, and does it increase the amount of disorder? Well, easiest thing to do is look at my energy. The energy here is on the product side, right? You took some reactants, here's your products. You are producing heat, so the heat is being given away. So this is exothermic. And we said exothermic is a vote for spontaneous. While we're at it, let's do the next one too. Next one has carbon plus sulfur turning into carbon disulfide. The heat here is a reactant. If it's a reactant, that means the heat is going in. So this is an endothermic reaction. And if heat is going in, we are increasing the energy of the system. Everybody likes to be low energy, not high energy. So this is a vote against. Okay, the change in the enthalpy is easy, right? All you have to do is decide exothermic versus endothermic, vote for or vote against. The hard one is the change in entropy, disorder. Okay, so let's focus on this equation and let's figure out our entropy. Just like the last time, first thing you need to do is count. How many reactants versus how many products? I've got 1 propane and 5 oxygens, which gives me 6. On the product side, I've got 4 plus 3 is 7. So I'm going from 6 to 7. It's not a big change, but it is a change. And you are going from 6 to 7, so you are talking an increase in the amount of disorder. So this is telling me that my delta S should be positive. But we said the other thing you got to look for is phases. Is it a gas? Is it a liquid? Is it a solid? Is it an aqueous? And this problem is kind of like the last one, right? You started off with all gases. So in the beginning, everything is high chaos. And what do you end with? You end with everything that's a gas. So at the end, you're high chaos. So based on the numbers, you will get an increase in entropy, a little bit of an increase in disorder. Based on solid, liquid, and gas, you're going from all gases to all gases. That's not really a change, right? So based on solid, liquid, and gas, I would say the delta S is no change. So if one is saying that the delta S is positive and the other one is saying that the delta S is no change, then I'm thinking the delta S is positive. You are going to increase the amount of disorder. You are increasing the amount of entropy, and we know that the universe loves disorder. So that would be a vote for spontaneous. So exothermic, vote for spontaneous. Delta S being positive, vote for spontaneous. If you got 2 votes for spontaneous, spontaneous wins. So this reaction will be spontaneous. Now, if you have any experience with a propane barbecue, you know that this reaction is spontaneous, right? You turn the propane on in your barbecue, you light it. Once you light it, the reaction just goes on its own. You don't have to do anything to keep the propane burning, right? It just naturally burns. It spontaneously burns. All right, so let's look at the last one here. For the last one, we've already decided that the heat is a reactant, so it's endothermic, and we decided that that was a bad thing. Now, if we want to talk about entropy changes, you got to do 2 things, right? You got to count, and you got to talk about solids versus liquids versus gases. So if we count, here on the product side, I've got 1 carbon and 2 sulfurs. That's 3. On the product side, I've got 1 carbon disulfide. So I'm going from 3 things down to 1. That's not good, right? Because 3 can be fairly disordered, but 1 can't be. So this is telling me that my delta S here is negative. It's dropping, right? Disorder of 3 down to a disorder of 1, right? That's a drop. If I look, though, at the states, I start off with a solid and a solid. So my carbon is very, very organized. It's a solid. It has very low disorder. It has very low entropy. So this would be low entropy. If I look at the sulfur, it's also a solid. So it's also very organized. None of these little particles can move. And therefore, it would also be low entropy. But what is your product? Your product is a gas. Gases move very quickly. They move very far. These things have high chaos. This would be high, I should actually say very high entropy. So you're going from very organized solids, which is very low, to something that has a very high entropy. So the entropy is going to go way up. So this is telling me that my delta S should be positive, right? Low entropy to high entropy, positive. Okay, well, I've got a bit of a disagreement here. Number-wise, right, going from 3 down to 1 tells me my disorder gets smaller. But going from a solid to a gas tells me my disorder gets bigger. So these 2 effects are working against each other. So if I want to know overall, is this going to be a positive or negative entropy change, you got to decide which one it dominates. Now, if I'm changing from 3 to 1, that's like having a sock drawer. Let's say you got a sock drawer and you got 3 odd socks versus a sock drawer with 1 odd sock. Is there really a difference in the amount of disorder here? Like 3 socks can get all tangled up. So there is more disorder with 3 than if you have 1. Because if you only got 1 sock in the drawer, it can't really get disordered. So yes, there is a drop in disorder, but this is considered to be small. So this is a small negative. If you talk about solids versus gases, solid has this much disorder. A liquid would have less disorder, so it's a bit more disorder. Sorry. Solid has this much disorder. A liquid would have more disorder, so it's a bit higher. But gases are extreme. They'd be like way up here. If you go from a solid to a gas, this is a huge positive. So if you've got a small negative value and you're adding it to a huge positive value, your delta S is going to be positive. Okay, so that's one of the issues with this. When you're talking about your entropy changes, entropy has more than one factor going into it. And sometimes those factors are contradictory, so you have to decide which one's big and which one's small. Now, that leads us to a second contradictory point. We said this was endothermic, so that's a vote against. But I've decided that the amount of entropy change is going to get bigger. So this is a vote for. So I've got vote and vote against, and I got one vote for. If you've got opposing votes, again, you've got to decide which one is bigger. Because if the endothermic part is the most important part of the two, then this negative vote will carry the day. Like, negative vote will outweigh the positive and the whole thing doesn't work. If it turns out that your entropy is the dominant factor, if this is the most important, then the positive vote is the most important vote and it dominates over the negative and the whole thing becomes positive. Right? This is one of those where you're going to have to decide which one is more important. And for this particular problem, I really can't tell. So for this one, I would have to say that this one is unknown. Don't really know if this one's going to be spontaneous or not. And that's the problem of predicting these based on endothermic and exothermic, based on, are you going to go from 3 particles to 1? Are you going from solids to gases? Right? It doesn't have any numbers. So oftentimes you get opposing votes and you're not really sure how the whole thing is going to go. All right? So if this is the way that you are deciding spontaneous versus not spontaneous, then you have to realize that there will be cases where you're not going to be able to say for sure. Okay, and I've kind of summarized that in the final table here. If you are exothermic, that means your delta H is negative. Okay, this is my exothermic. If your delta H is positive, that would be endothermic. We had said exothermic good, endothermic bad. Now down this side here, I'm talking about the entropy change. We said if your delta S is positive, that means more disorder. That means you're good, right? This here would be more disorder. We said though, if your entropy change is negative, that means you have less disorder. So this one here is less disorder. And we said that's not good. So here in this first box, you got a vote for and a vote for, right? It is both exothermic and more disorder. If you've got 2 votes for, it's always spontaneous. This box here is like your double negative. You got endothermic, that's bad. You've got less disorder, that's bad. And if you've got 2 down votes, this one's never spontaneous. But the other 2 combinations are the ones where you're going to have trouble. Where you're going to have a no vote, but also a yes vote, right? More disorder, but endothermic. Which one wins? Or down here, it's exothermic, but there's less disorder, right? Which one wins? So for these problems here, you will hit situations where you're going to have to make a judgment call, or you're just going to have to say, I don't know. Now, the better way to do this is by actually putting numbers with the delta H's and putting numbers with the delta S's and calculating a thing called Gibbs free energy. Because if you calculate the Gibbs free energy based on numbers for these two, then it's a lot more definitive. Negative Gibbs free energies are always spontaneous, and positive Gibbs free energies are always non-spontaneous. And if your Gibbs free energy equals 0, you have an equilibrium. Right, so oftentimes we'll use this as kind of a rough draft of deciding what's spontaneous or not. But what we really want to do is move into numbers because the numbers are a bit more definitive, right? There's no more of this question mark business. So I do have a video that talks about determining spontaneous or not spontaneous using Gibbs free energy. So if you're interested in that, you might want to check out that video as well. And once again, thank you for joining me here at Chemistry with Dr. Clark.